On behalf of my co-investigators, I'd like to present some results of our project. These are the design results of a compact, low cryogen, head-only 7 Tesla scanner for brain imaging. 7 Tesla MRIs today are characterized by whole body scanners, which are fairly heavy, require significant amounts of liquid helium, occupy a large space, and have modest gradient performance. Because of these considerations, major investment is needed in terms of installation systems costs. And gradient performance really is limited because you really need high power amplifiers, which are limited really by how much power you can put into a system. In addition, whole body systems are limited by peripheral nerve stimulation. So we have approached this in a different manner. Our Compact 7T has an objective of substantially reducing the magnet weight down to about 8,000 kilograms to a mass comparable with whole body 3T scanners, and with only 18 liters of liquid helium. So no additional floor reinforcements required, no vent stack is needed. In addition, because the fringe field is designed to be within the 3 by 5 meter space of a whole body 3T, the magnet can fit into an existing clinical 3T bay without any modifications. Because this is a head-only device, we're able to utilize fully slew rates up to 820 Tesla per meter per second with simultaneous gradient amplitude of 140 Tesla per meter on all 3 axes. Overall, this will have much lower total cost of ownership than a whole body 7T system, making this more accessible to more sites so that we can expand brain imaging to a larger number of locations. In addition, the electronics is a part of a product electronics commercially available setup so that we don't need to do much modification to the system electronics and receiver chain, and it will be almost identical to that of a conventional 3T scanner. The motivation behind all this is in the imaging performance. On the slide on the bottom shows the peripheral nerve stimulation thresholds for a whole body system shown in green and 2 head-only systems that we have built. The head-only compact 3T indicated by the orange line and the head-only magnet system indicated by the blue line. As you can see, for whole body systems, the parameter space that's accessible is fairly limited. You have to have a very low slew rate to be able to utilize high gradient amplitude. But in order to use the high slew rate, you're limited by much lower gradient amplitude, especially for echoplanar imaging. However, for head-only scanners, the peripheral nerve stimulation threshold is about 5 times that of whole body gradients. As such, the parameter space is much larger, allowing more flexibility on the imaging. More importantly, since the maximum gradient amplitude on EPI scans is no more than 5 Gauss per centimeter, we are fully able to use the maximum slew rate of these systems. This can be seen here in EPI images on the bottom left. At a slew rate of 200, we can achieve an echo spacing of 736 microseconds, and this leads to the expected or the typical signal loss and geometric distortion, especially in the areas of high susceptibility. At 700 Tesla per meter per second, the echo spacing can be reduced to about 390 microseconds, which is about half. And here you can see the areas of signal loss in the areas of high susceptibility are significantly reduced. So this means that imaging, for example, in areas of the hippocampus, which is typically characterized by signal loss, can be avoided. The shorter echo spacing also allows higher SNR because you can elect not to use parallel imaging, which gives you an SNR advantage there. Another advantage of the head-only systems, and also it's for 7T, is for diffusion, for microstructure imaging. We need high gradient amplitudes to achieve shorter TE times for high B-value imaging, trying to differentiate diffusion between free diffusion and also restricted hindered spaces. So here you can see whole body 3T has fairly long minimum TE times as a function of B value. As we proceed using head-only gradients, the TE times start to reduce. With the compact 3T scanner, as you can see here on the blue curve, you can see a drop in the minimum TE times. However, the most significant reduction in the minimum TE time comes when we compare whole body 7T scanners with the compact 7T and also the magnet system. You can see almost about a factor of 2 reduction in the TE times. This leads to higher image signal to noise ratio at the same B value. So you can see 2 examples here. This high signal to noise ratio can be used to achieve higher spatial resolution imaging. Here, 1 millimeter isotropic diffusion at a B value of 2000. And here's 1.5 millimeter isotropic with 40 directions at B value of 2000. Another use of the high slew rate, high gradient amplitude system is in moving from single echo EPI for fMRI to multi-echo fMRI, where we're using the R2 star maps to do the analysis for functional activation. R2 star maps have a much better, closer representation of the cerebral metabolic oxygenation rate, and is not confounded by effects of perfusion. So as you can see here, the difference between a system with a slew rate of 700 versus a slew rate of 200, you can see that the minimum TE times achieved for the 3 echoes is significantly lower than that for a whole body system. So what this allows you to do is get better SNR fit of the R2 star maps, allows us to achieve shorter acquisition times per slice. So for a given TR, we can have more slice coverage or achieve a high temporal resolution for the same slice coverage. So in terms of patient handling, the gradient that is being designed or has been designed for the compact 7T is an asymmetric gradient, as in the compact 3T and the Magnus. The form factors are the same. So the patient patient accommodation acceptance then will be similar to that of the compact 3T and Magnus. Both of these systems have run through probably several hundred patients already, so that we know that the level of acceptance is high. So even though we have a smaller diameter, in this case 42 centimeter bore of the gradient, we do not expect any issues with patient acceptance. In terms of the magnet design, this is a standard 8-coil design, 6 main coils and 2 bucking coils. The salient feature here on this 7T compact magnet is that there is no solenoidal coil, and that substantially reduces the weight of the system. We're using rectangular wire, which is much easier to wind. This is conventional Niagan titanium superconducting wire operating at about 450 Tesla. As you can see from our design specifications, we've met all the design specifications, mostly. And the magnet length and form factor is, again, almost the same as a conventional whole body 3T scanner. The salient features of the design here is that the stored energy is about 16 megajoules using about 86 kilometers of wire. The conductor weight alone is about 2,100 kilos, and the rest of the magnet weight is the support structures, the vacuum vessel, and everything else that goes in. Magnet ride-through, let me talk about that. That's relevant to the magnet cryogenics. So this is a low cryogen system with 18 liters of helium at 4K, operating roughly about 3.5 Kelvin. The cryocoolers are RDE 412s, which provide a total of 1.5 watts of cooling power at 3.4 Kelvin. So if one cryocooler fails, the magnet remains operational. If 2 cryocoolers fails, we have about 6 hours before the magnet runs dry. And if all 3 cryocoolers fail, it's about 2 hours before the magnet runs dry. Because of this configuration here and the magnet heat load, The magnet can be ramped from 0 to 7 Tesla in about 9 hours. As you can see here, here's the rise in coil current, and here's the corresponding drop in helium volume and the corresponding rise in temperature. And as you get close to 450 amps, we end up basically recovering, liquefying back the helium. This is a closed system again with 3 coil heads, and the helium tanks would cycle or recover the helium. So the important consideration for us is magnet gradient interaction or the magnet heat load. To understand the heat load, we used the compact 3T scanner as a test platform. We injected 1 watt of power into the large coil and observed the temperature rise. So this would then be fitted into our model to verify and validate the model. So our model then would allow us to understand the Joule heating due to typical gradient activity from equiplanar imaging, which is important for DTR or fMRI, and then simulate the power deposition in the large coils and estimate the temperature rise. So this is important to make sure that the coils are cool to below the temperature that will quench the magnet. So in this example here, our temperature gradient simulation shows the temperature distribution along the coils, or a section of the coils, where we injected 2 watts of power into the coil support structure and about 0.3 watts each on the large coils. So you can see here the temperature rise in this case is about 0.2 Kelvin. Okay. The measurements here would give us an idea of how the magnet will perform when it is run heavily, and ensuring that the overall temperature remains below 4.5 Kelvin. Oh, okay. The magnet is under construction. This gives an example of the different steps in terms of winding one of the coils. This is the large coil. You can show the bobbin, the bobbin, the electronic control, wire spool, and here is Gene Conte, one of our technicians, winding the magnet, applying epoxy as he goes, and then putting the whole assembly into liquid nitrogen to remove the bobbin, and then here's the finished coil. In terms of the program timeline, we started the program in late 2018. We spent the last year and a half designing, validating, and simulating different aspects of the magnet in terms of structural stresses, the cryogenics, and also specifying what type of wire we needed. We expect to produce the first image on this system in early 2022, and then in the latter half of 2022, installing the system at UCSF and begin our clinical evaluation. At this point, the HG4 gradient coil is under construction. We also have begun a supplementary study looking at Alzheimer's study on the magnet system to work out the kinks on the acquisition. When we have the 370 magnet ready at UCSF, we'll be testing it there. So this project really is a culmination of evolution of different brain imaging systems, beginning with a cryogen-free compact 3T magnet, which was installed at Mayo Clinic in 2016. This moved on to a higher performance, high efficient Magnus 3T MRI system that was recently installed at Walter Reed. And then the image on your right shows the compact 7T mock-up that we built in the lab just to test patient compliance and patient acceptance. This is a mock-up of the gradient in a styrofoam model of the magnet system. Again, we expect it to be installed at UCSF and the latter half of 2022. I'd like to acknowledge a very large and diverse multidisciplinary product team. I'd like to acknowledge my co-investigators, Dr. Xu at Mayo Clinic and Dr. Xu at University of California, San Francisco. There's a large number of people involved in the project, and I thank you for your attention.